We're going to talk about alternating series. We've been looking for the most part at series that have been positive and decreasing, like 1 over n. And we can look at their partial sums. Typically, their partial sums, you know, we have, after one term, we have 1. And then 1 plus a half would be 1 1/2. That'd be plus the second term. Plus a third would give me like 1.8333. Plus like 1/4 would give me, you know, something over 2. And what we can discover if we use our calculators, if we have our ability to use our calculators, is that your calculator does summations and nth partial sums. And it might be an easy way to check to see if things are converging or diverging. If you go to math 0, you see summation. And you can type in, you know, n or x starts at 1, goes to, let's see, 1, 2, 3, 4, 5. Let's just do the 5th partial sum for 1 over x. And you can see we got 2.28. Great. So we continue to increase here, and we'll continue to increase. And we find that for 1 over n, the nth partial sum will never approach a value. It will never have a limit. You can kind of confirm that if you look at the, you know, 50th partial sum and the 100th partial sum. So here's the 10th partial sum. Here's the 20th partial sum. We go through 2.92, and then we go to 3.59. I go up to 50th partial sum, 4.49. Maybe we were converging towards, you know, 4.5. But then I go to the 100th, and I get 5.18. So what we find is, though we will grow slowly, we will continuously grow with 1 over n. But if we looked at, you know, 1 over n squared, you can kind of see that there will be some limits somewhere where the partial sums will approach that limit. Okay, and we can confirm that using our calculator, math 0. X starts at 1, goes to, why don't we just do 20 of 1 over x squared. And I got 1.59. I can go to 100 and see, are we increasing or are we approaching a value? 1.63, it is increasing, but it's increasing slowly. Let's go to 200 and see if we can get that, or if it, sometimes it overloads in terms of how much you could plug in. Great. So 1.6399. So you can definitely see that it's starting to slow down, and it will be approaching some value, not above 2, but more like, you know, here. And the partial sums will just start here, and they will continue to increase, and hopefully they will increase at a slower and slower rate until they approach a specific value, whereas this will not have a limit. All right. Well, let's look at series like this that alternate in sign, -1 to the n plus 1 over n. Let's write out some of the terms. If I plug in 1, I have -1 squared, which is positive 1 over 1, so that's 1. But if I plug in a value like 2, it becomes -1 to the 3rd power. Well, that would make this entire thing negative. So it'd be -1/2. So I'd be subtracting a half. I plug in 3, it goes back to being -1 to an even power. It'd be -1 to the 4th power. So then all of a sudden it would change signs back to being 1/3. And then it'd be -1/4. Then +1/5. Et cetera, et cetera. Okay? The fact that we have some -1 to some n power, you'll see n, n plus 1, n minus 1 in our thing, or just really any number to the nth power, as long as we have a negative with that, all of a sudden, because we're doing odds and even powers, we will see that most likely our guys are going to alternate. Okay? Well, let's look at the partial sums for this guy. And let me switch this to 1.5. And it's really interesting how they appear. So we start with our first term's partial sum as 1. And then we subtract a half, and we go from 1 to a half. Very cool. Well, I'm not going up like I'm used to. But then I add a third. So I have 1/2 plus 1/3. So I'm going to have to pop up here to plus a third. So this was minus a half and then plus a third to go from there to there. Thing's running out of juice. Yep. And then I have to subtract a fourth. Well, I'm going to go and end up right around here when I subtract a fourth. I'm not going to move as far as subtracting as adding a third, but I will be moving and subtracting a fourth. Then I add a fifth. I end up here. Okay? And you should start to see the pattern with this alternating series and its partial sums. Okay, and these are partial sums, right? So if this approaches a value as n approaches infinity, then this converges. Do we think this is going to approach a value if I continue the trend of adding the next term and the next term and the next term? Good. I see some head nods. Because we would see that we'd go a little bit down and then back to being a little bit up. But then we'd go less down and then less up and then less down and then less up. And we would be approaching this line here that I will shift. This would be the limit as n approaches infinity of s of n. This shows that we will this shows that this will converge. Its partial sums will converge towards a number. Because each time I add and subtract one, I just keep bouncing up and down across the number until I'll just be really, really close to, but just barely above, barely below, even less above, less below. Okay? So this is interesting. This is like the harmonic series, 1 over n. Well, 1 over n does not converge. It does not approach a value. But 1 over n squared does. But all of a sudden, if we alternate the signs, we definitely converge. Okay? Now, let's look at another one. Well, we know that we would be trending our terms towards 0. If I can write out the terms, I'd have 1 minus, plug in 2, it's 1/4. Plug in 3, it's 1/9. Plug in 4, 1/16. We will find that the same thing occurs. I'd start at 1, subtract a 4th, add a 9th, subtract a 16th, add a little less, subtract a little less, add a little less, subtract a little less. And we can see that my partial sums will approach this value, which ends up being like right in the middle of the bounces. So this will definitely converge. Well, let's look at this guy, and let's figure out if this guy converges. Okay, 1/3 minus 2/5 plus 3/7 minus 4/9 dot, 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 dot. What do we think? Is this going to converge? We're going to say no. Why do you say no? Why are your instincts no? Good. As I have n approach infinity, what does this trend towards? This term without the negative 1? It trends towards 1/2. What we will find is that we'd start with 1/3, and then we'd be moving back and forth, and you'd be like, oh, this looks like it's going to converge. But what ends up happening is as we continue to go on, we would pretty much be staying close to adding and subtracting 1/2 every single time. So we would never get closer and closer to the value, which you could see in the middle, because each time we'd end up essentially adding and subtracting 1/2. Which just shows you that the nth term test for divergence still works. This limit as n approaches infinity of n over 2n plus 1 ends up equaling 1/2. I don't even look at the negative 1 over n. I know that since we are, alternating and adding 1/2, subtracting 1/2, we will never approach a specific Sn. We will never really converge towards it. So we are going to diverge. All right? Great. Most alternating series do converge. It's very simple for an alternating series converge. We just looked at the harmonic series converging if it alternates. All you need to occur is you need this series to be alternating. So make sure we say that it's alternating. So that's, plus, minus, not plus, plus, minus, minus, unless it's rewritten, but, nothing kind of crazier than that. The limits as n approaches infinity of your series must equal 0, just like we've talked about before. We must be eventually adding smaller and smaller values or subtracting smaller and smaller values. And a sub n must be decreasing in its values every single time. We'll say the absolute value of a sub n is decreasing in its values. We need to be approaching 0, but in a fashion where our first derivative is negative always. Else we'd be bouncing all over the place around a number, and we would not be approaching, that S of n. I actually might have to shift, that S of n value, the middle. Okay? Typically, you will see in your textbook that a sub n plus 1, which is just like the next term, has to be less than a sub n for all n values. And we use the absolute value so that we don't think about, positive versus negative. It must be less than. It's literally just make all the values positive, make sure they're decreasing. The next term needs to be less than the previous term. Less than previous term. Don't put the equals to. Okay. Now, let's look at this series. Does this series converge? It's just negative 1 to the n plus 1. It's 1 minus 1 plus 1 minus 1 plus 1. Do we think that converges? No, you are correct. No. You think about the partial sums, they pop between 1 and 0. They will not converge towards a value. Also, the limit as n approaches infinity is not 0. So no. Okay? So we know that. That's good to know. Let's look at this. Negative 1 to the n plus 1 times 1 over the absolute value of sine n. So it ends up being 1 over sine 1 minus 1 over sine 2, as long as it's absolute value, it's like positive, plus 1 over sine 3. Will this converge based on our knowledge of the alternating series and its convergence? It looks like our denominator is getting bigger, right? Sine 3, sine 4, sine 5, that's got to be getting bigger. Our numerator is staying the same, so it looks like we are decreasing in our values, and we're alternating. So logic tells us we must be converging, but I made an error in my statement. What's my error? Yeah, sine's not increasing as I go on. Sine of 1 could be bigger than sine of 2. It could be less than sine 2. So no. One over sine of n plus 1, not necessarily less than 1 over sine of n. Okay. Same thing could be stated for this guy. We got n plus 1 over log of n plus 1. In this situation, we would say no, but by the nth term, the limit as n approaches infinity would approach infinity. N plus 1 will be growing faster than the log of n plus 1. So no. Okay. Interesting to see that we've already talked about some of these alternating series. We talked about geometric series where the r is just between -1 and 1. In this situation, we can write this as -1 to the n times -1. And that's over 3 to the n. And that could be written as -1 over 3 to the n times -1. And that checks. That's definitely convergence. This is a geometric series with r between 1 and -1. Okay? But now you could say this series converges by the alternating series test. All right? So we have two possible ways to show that that converges. Now, let's talk about the remainder theorem. We just had that great picture of our sums popping back and forth and back and forth and approaching my actual sum, which we will call S. Might be 3D. Works out well. Okay. S, we would say, is our actual sum, our true sum. What's really interesting is when we add and subtract these values, we will always pop over the sum. Okay? We'll pop over it on the high side when we add, and we pop over it on the low side when we subtract. When you guys watch the rest of this video, we'll talk about how we can set bounds for what the sum is just by looking at whether or not we added a term or subtracted a term and understanding that, oh, my sum has to be between those two values. So watch that, and we will, there's some other stuff about absolute and conditional convergence, so please watch that and do your homework. So really, all I need to do is understand if I add or subtract the next term. Well, if I added the next term, so plus the 1/3, I'm going to end up with a value that is above the actual sum. If I subtract the next term, I know that I'll bounce over the sum and end up with a value that is less than. Okay? The actual value will be somewhere in between. You know, we'd add a smaller value. We call the difference between the term and the actual value the remainder. And it's the difference between my partial sum and my actual sum, which is s. And that actual sum is right here. We can see visually, and this would be equal to the limit as n approaches infinity of my partial sum. Okay? So it's important that when you're finding upper and lower bounds, you got to think, if, I'm going to get rid of this because I don't need it. If you are adding your next term, then that term is going to be greater than your sum, and your previous term is going to be less than the sum. So you know that your sum is between those two. And if you are subtracting the next term, well, then you know that next term that you subtracted is going to be less than the sum, whereas the previous term is going to be greater than the sum. So depending on which way you're going, you know definitively, hey, that's going to be less than, and that's going to be more than. A sub n and greater than a sub n plus 1. Okay? That's good. What also do you know? Well, you also know that the remainder that we have between our sum and our actual, our partial sum, the remainder is going to be less than how much I'm subtracting or how much I'm adding. Okay? I know that I'm going to subtract 1/4. I'm going to go beyond s and get to that value. And then if I add 1/5, I'm going to go above s and get that value. So we say that the remainder will have to be less than the next term that I'm adding, or subtracting. If I'm subtracting 1/4, well, I will go beyond s. The remainder is less than that. So kind of going on to this is this remainder theorem, the alternating series remainder theorem. It states that if we take our actual sum and subtract our partial sum to get our remainder, that remainder is going to be less than the next term that you're adding or subtracting. Okay? And we do absolute values. That way we talk about just positive remainders and positive differences. We know that remainder, the actual value is going to be really in between your previous one and the next one, whether the previous one is less than and the next one is greater than, or vice versa. Okay? That's remainder. And this is the next term. I don't like to use this that often. I find it confusing. I like to set bounds, and as long as you understand the bounds, and as long as you understand this picture about how you're popping up and over your actual sum with your partial sums, you will be able to understand any question thrown at you in terms of these remainders. So let's take a situation like this. We're going to find a lower and upper bound for this sum using our fourth partial sum. So S sub 4 would mean the fourth partial sum. So I need to figure out what is, and I'll plug in 1, 2, 3, 4. 1 minus 1/4 plus 1/9 minus 1/16. And I need to figure out what that is. I could use a summation, but I probably am just going to be better off if I a little frozen here. Be better off if I just do it in my calculator. Okay, second. Quit. So 1 minus 1/4 plus 1/9 minus 1/16. Okay, I get 0.7986111. Okay, now the question is that going to be below or above my actual sum? Well, since I subtracted the last term, think about our partial sums. We start with 1, we subtract a fourth, we'll go over it, add a 1/9, then we subtract 1/16. I know that this value is definitively going to be underneath my sum. Okay? But now, where is the upper bound? Well, I know what the next term is going to be. I'd be adding 1/25 if I plug in 5. Okay? So when I add 1/25, I'm actually going to be adding more than, I know that my actual sum will be within this 1/25 that I'm adding. And let's take our value of 0.798 and add 1/25. And I know that we will be between this value and 0.8386. Okay, and we can keep looking at that, and you can actually find that the partial sum, the actual sum, is pi squared over 12. If I calculate pi squared over 12, it's fascinating that pi is involved here, we can see that the actual value is 0.822, which is between these two values, and we understand that we're getting closer to our sum each time we're adding and subtracting, and my remainder is between, so the remainder so that minus that, or s minus this, has to be less than 1/25. Because I'm adding 1/25 and I pop over, whereas my remainder is right there. Okay? That's the whole alternating series remainder theorem. And we can add this to see exactly how much we're adding and subtracting. Okay? Next question. Show that this is less than 1/2. Okay, so let's just write out a couple terms. We have the sum n starting from 2 to n of -1 over -1 to the n over 1 over n log n. So I plug in 2, my first value is 2. I get 1 over 2 log 2. And then I would alternate, it'd be minus 1 over 3 log 3 plus 1 over 4 log 4, et cetera, et cetera, et cetera. And how can I show that that is less than 1/2? Well, I start by understanding that 1 over 2 log 2 is going to be an upper bound, right? And because that starts with a plus. I started with a plus. So if I think about my partial sum, I start with this positive value. And then I subtract 1 over 3 log 3, add 1 over 4 log 4, subtract, add, subtract. So that's this first partial sum here. And 1 over 3 log 3 would be that second partial sum. So I know this is actually an upper bound. Well, immediately I know that 1 over 2 log 2 is less than 1/2, right? And I know the sum must be less than that. And I know the sum will have to be greater than 1 over 2 log 2 minus 1 over 3 log 3. Or we could say the sum, that the remainder, the difference between this term and the sum is less than this. But immediately, this is what you can say. Since you started with the plus, this will be an upper bound to your initial sum. This upper bound is less than 1/2. This sum, we can say, also is greater than that. So boom, we just showed that that sum is less than 1/2. Finally, we'll go to absolute versus conditional convergence. It's very simple, and if we understand all of our rules coming up to now, just an application of those rules, including the alternate series rule. We'll say a series is absolutely convergent if we start out with the series being convergent and if we took the absolute value of it and we only had positive terms, we'd also be convergent. That's simple. And if we are conditionally convergent, we will say that my original series convergent. However, the absolute value, so all the positive terms added together, is going to be divergent. Okay, this is conditional versus absolute convergence. Now let's look at a couple. We'll confirm if the alternating series is divergent, conditionally convergent, or absolutely convergent. Typically, when we talk about things being conditionally convergent, it's only when we're talking about about alternating series. Because if A of n is positive all the time, well then it's convergent. Well, definitely it's going to continue to be convergent if you're taking the absolute value. But the question is, if A and m is alternating, the question is if that alternating series, if they're positive and you're adding them together, is that going to be convergent? Okay? And we will find very simply right away that no, we won't always have, well, it'll be easy to figure out which ones are absolute and conditionally convergent. The easiest one is 1 over n. Well, negative 1 over n, we know that this is convergent. By the alternating series test. It is decreasing in terms of its absolute values, and it alternates. And the limit approaches 0, so it converges. However, if I took the absolute value of this, so the absolute value of A and n, well, all you have to do is whenever you have an alternating, just make them all positives. The negative 1 would really just go away and become 1 over n. And we know that this sum is divergent. Because it's convergent, because it's an alternating series, but it's divergent when it is looked at in the positive manner, we would consider this series conditionally convergent. Okay, a couple more. This guy, well, if I look at the terms, they're going to be decreasing in manner. The next one, root 2, root 3, root 4, is going to be bigger in the denominator. The numerator is just going to be 1. So this is going to be decreasing. Its terms will trend towards 0. So we definitely converge because of the alternating series test. However, we look at the absolute value of negative 1 to the n over root n. This would turn into 1 over n. 1 over root n. And if we look at this sum, and starting from 1 and going to infinity, we know that this diverges. Why does this diverge? This diverges because we have a power which is less than 1. So here's another conditionally convergent series. Okay. Let's look at this one. I don't want to look at this one because it's got that log. That log does not help things. I feel like we'd have to use UDV to find the antiderivative and go through the integral test. Gross, but let's do it anyways. So we know that the denominator is going to be increasing. The numerator is going to stay the same, so it's going to decrease in terms. So we know this is definitely an alternating series that converges. Now, if I look at the absolute value, which would be 1 over log n plus 1, does this converge or diverge? I'm assuming this diverges, and I'm pretty certain that it does diverge. I think we have to use the integral test from 1 to infinity of 1 over ln n plus 1. I think I have to set u equal to ln n plus 1 and dv equal to dn. du is equal to 1 over n plus 1 times dn. V is equal to n. Ugh. That's gross. Let's not worry about that one. Just know that it converges. It probably is a conditionally convergent. This guy, however, this would be absolutely convergent. Why is it absolutely convergent? Well, it's an alternating series and is growing. Numerator staying the same. So we're decreasing. It's changing signs. Boom. Convergent by the alternating series test. And then if I looked at 1 over n cubed, this is also convergent. Why is it convergent? It's a p series with p greater than 1. Okay? That's it. That's alternating series. Thank you.